Hi everyone. My name is Steffi Olesi Muhanji. I am a PhD student at Dartmouth, and today I will be presenting on the case study results for an energy water nexus project that we did for the ISSST New England system. Oh no, 1 second. Okay, great. So I already talked about this, and just a bit of overview. I am a graduate student in the Laboratory for Intelligent Integrated Networks of Engineering Systems at Dartmouth. And what we do as a lab in a high level is study large scale engineering systems like the power grid, the transportation system, smart city. And we write models on how these systems are operated and controlled and some of their decision-making mechanisms so as to influence policy decisions and all that. And sometimes we integrate multiple networks to see how different synergies are, what kind of different synergies are there and how we can improve those and to reduce cost and to improve the technical performance of both of these things. So we have five main research areas, and this talk is going to be on the energy water nexus work, and it also intersects with the smart power grid work, but we've done work in electrified transportation, industrial energy management, and integrated smart city infrastructures. So as I said, the goal of this study is to highlight the results from the ISSST New England Energy Water Nexus study. And my presentation is going to have some background of why this was important and a bit of an overview of the New England power system data, as well as the methodology and some of the assumptions that we had to make for this study. And then finally, we will highlight some of the case study results and conclude. So in the past, the electric power grid was generally made up of a few large-scale thermal generating facilities that were very easy to control, and you had demand which was generally passive. But as we go to the future, we see that most of these thermal units are being retired, like coal and oil units, as well as nuclear retiring, and they're being replaced by solar and wind generations, which are more variable in nature. And so we see that the dispatchability or controllability of the generation system becomes a lot more variable, and therefore we have to start looking for new ways to control the grid to reduce the system imbalances that are introduced by the variability of solar and wind. Just to give you a sense of some of the challenges that an independent system operator would have to deal with is this dispatchable generation would generally have to track the forecasted net load. So on the day ahead market, the independent system operator would obtain the forecast for the demand for the next day, as well as the projected solar profile, as well as wind. And the net load here is the difference between the projected demand minus the wind and solar profile that you expect for the next day. And as you can see on this chart, the forecast and the actual demand are not always matching, and therefore you have these dispatchable generators that are needed to ramp up really quickly in order to track the net load in the real time. And another one of these issues is the dark curve phenomenon, where the black curve here represents the actual demand on your system, and every subsequent layer is an addition of X amount of solar into your system. And so you see, as you add more solar to your system, the belly of the duck grows, and the bottom of this belly represents the point where the sun is starting to set. And you have a lot of generators are offline and people are going back home and they're turning all the electronic devices online. And so the demand is also increasing. And so you have to bring these generators back online and ramp very quickly in order to meet the rising demand or the generation that's being displaced by the setting sun. And so it really complicates the capability of dispatchable generators to track the net load as you add more solar to your system. So in order for system operators of the wholesale markets like ISO New England to ensure the reliability of the grid, they generally acquire operating reserves as excess capacity that they can use to ensure that they are still able to meet demand despite the imbalances that are caused by stochastic generation resources. And so I will be talking about the load following reserves, ramping reserves, and regulation reserves. So load following reserves is generally defined as the excess capacity of the online generators to move up or down. So it's consider that you have a 500 megawatt thermal power plant with a lower capacity limit of 200 megawatts. So this plant can generate is currently generating 400 megawatts of electricity. So this plant is able to provide you with 100 megawatts of upward load following reserves, meaning that it can go up an extra 100 megawatts, and it can also provide you with 200 megawatts of downward load following reserves, meaning it can go down 200 megawatts. And load following reserves are acquired in the day ahead market to help track the net load variability and certainty in the real-time market. Another quantity is the ramping reserves, and this here is is defined as the excess ramping capability of the aggregate online generation fleet, and this is the capability to move up or down per unit time. So consider the same generator that we just had on the previous slide that is currently producing at 400 megawatts and has an upper ramping capability of 50 megawatts per hour and is currently scheduled to ramp for 25 megawatts per hour and has a lower ramping limit of minus 60 megawatt per hour. So in terms of ramping reserves, this generator is able to provide an additional 25 megawatts of upward ramping reserves and 85 megawatt per hour of downward ramping reserves. And again, these reserves are used to help track the net load and variability and uncertainty during the day. And then finally, regulation reserves here are slightly different from load following and ramping reserves in that they are more of a real-time automatic feedback control capability that some generators have, and they just use to move up and to track load and move up and down as needed in the real time. So regulation reserves tend to act at a much faster timescale compared to load following and ramping reserves. And again, this is used to respond to net load variability and uncertainty. Now on to my second part of the presentation, where I will be talking about the New England Energy Water Nexus study, the data, the methodology, and some of the assumptions we made for this study. So we've seen that as we increase the amount of variable renewable energy resources like wind and solar into the grid, we have to start thinking about new ways, new control levels and ways to manage imbalances on the grid. And demand side resources or demand side management is seen as one way to do this. For this study, we considered water treatment and wastewater treatment facilities as having the capability to provide either load shifting capability or load shedding capability in order to help balance the grid in the real time. And so the reason why we looked at this was, here is a map of New England, with ISO New England states, where Maine, New Hampshire, Vermont, Massachusetts, Connecticut, and Rhode Island. And this map here represents all the power plants in the region, as well as the rivers. And as you can see, majority of these power plants are located near a water source, just showing you how strongly coupled the two systems, the water and the energy systems, are. And with this, we were able to study how different hydro or energy water resources, so for example, hydro facilities that provide electricity, and water and wastewater treatment plants that consume electricity, as well as thermal power plants that consume a lot of water for cooling purposes. So we use the electric power enterprise control simulation to assess the electricity side of things for this study. And just this diagram here represents the structure of the Epec simulator. This is a 4-layer simulator with 3 optimization markets. The first one is the day ahead scheduling, resource scheduling market, which is essentially a unit commitment that determines what generators should be online for the next day in order to meet demand and at what time. And then we have a same day resource scheduling market, which is another optimization problem, whereby it happens, this optimization problem is carried out in the day of, and it runs every hour with a 15-minute time step to determine what generators that can start very fast within 10 to 30 minutes should be online to meet changes in demand in the real time. And then finally, we have a real-time balancing market, which is essentially an economic dispatch problem, whereby you have a set number of generators that are already online and you are tracking the demand in real time. So what you do is you might have to increase the output of those generators or reduce the output depending on how the demand is changing in the real-time market. So the real-time balancing market happens in a timescale of 5 minutes. So as you can see, we have 3 layers of optimizations, all occurring at different time steps, and to capture the different imbalances that are happening at the different time steps that we're dealing with. So we have a day, we have an hour, and we have 5 minutes, and we have the regulation service, which acts at a much faster timescale to clear out the imbalances that were not cleared out by the real-time balancing market. And in order to incorporate ISO New England market operations, we modeled these simulators so that it could have a same-day resource scheduling, which is an optimization program that is specific to ISO New England operations. So, as Priya had mentioned, it's generally complicated for system operators to release critical infrastructure, energy infrastructure data to, universities and all that. So this study was based off of a renewable energy integration study that we conducted in 2017, and a lot of the data for this study came from that study, and it was the data was grown to 2040 scenarios to allow us to study the system based on the requirements of the funding by the DOE. And when we carried out the study in 2017, ISSST New England stakeholders agreed on using this zonal representation of the system, whereby we have this bubbles which represent the load areas, the different load areas in New England. And so we were able to abstract the system into this simplified model, and we introduced interfaces to address line congestions within the system. And then we implemented a lossless DC power flow analysis to help us determine the flows of power between the different load areas. And so in total, we had 13 zones, which are the circles in the diagram, with 21 interfaces and tie lines. In order to assess the physical flows within the energy water nexus, we assumed the yellow system boundary in this diagram, whereby we can quantify the flows through the boundary from the fuel mining, water supply, wastewater management, as well as the natural surface environment. And by using a pipe and bubble approach from the previous slide, you can find that all this wastewater treatment and water treatment systems would fall within a given bubble or load area. And therefore, we did not have to do a full-scale hydraulic modeling to achieve the same goal that we wanted to achieve, which was to assess the flexibility that the water infrastructure can provide to the electricity infrastructure. And so given these assumptions and the methodology, we worked with Amro to using their Reed's capacity expansion model to come up with, to determine how the New England system will look in 2040. And these are the scenarios that we considered. We considered 6 scenarios, whereby the third scenario had a significant amount of variable renewable energy resources. And the fourth scenario was our business as usual scenario. This is a scenario where if we continued, if the New England system continued at its current trajectory, how this scenario represents how it will look like in 2040. And in our system, we had 3 different kinds of energy water resources. And the first one was run-of-river and pond hydro power profile, where we had a penetration of about 6 to 7% of the system peak load. And then we also had pump storage capacity of about 6% of the peak load in the system, as well as water electricity demand from wastewater and water treatment plants. For the study, we treated flexible water resources as having a load shedding rather than load shifting capability. And our run-of-river hydro and pond hydro could be curtailed at a cost of $4.5 per megawatt hour, and flexible water resources in general were assumed to be able to contribute towards operating reserves. Due to some assumptions that we had to make for the ISSST New England study that we did in 2017, we assumed that pump storage will be, we treated pump storage as a dispatchable resource throughout the study. So we did not change how it's operated for all the cases that we worked on. And this here represents the final capacity for the final installed capacity for the different fuels. And as I mentioned, scenarios 3, 6, and 2 had significant amounts of solar and wind installed, and therefore they were considered to be to have high penetrations of renewable resources. And scenario 4 was the business as usual resource, and you can see that the solar and wind penetration is not nearly as high. And this figure represents the demand profile for two of scenarios. The first one is the business as usual scenario. And what I would like you to get from this slide is that for the business as usual scenario, once you subtract the available solar and wind resources in your from your system load, you find that the demand is still above zero. But for the scenario with high penetration of wind and solar, when you subtract your variable generation from the demand, you see that for most of the year, especially in the fall and in the spring, your overall demand is going to be less than zero. And this is a challenge because it means that you would either have to curtail a lot of your solar resources, solar and wind resources, or you would have to shut down a significant portion of your generation, dispatchable generators, in order to continue tracking the net load. So on to the results for the study. We considered two operating modes. One of them was the conventional operating mode, whereby we did not have any flexible water resources. And the second one was the flexible operating mode, where we had some run-of-river resources in the system, as well as wastewater treatment plants that had a load shedding capacity, and run-of-river and pond hydro could provide operating reserves. And to measure the reliability value that we get from coordinated energy water nexus operation, that is in this flexible case, we looked at how well these two operating modes perform in terms of available reserves in the system, in terms of how much load following reserves we have, how much ramping we have, is regulation used up completely, and how much is curtailment used as a control lever in the system as a whole. And then we also tracked the imbalances in real time to see how they compared for the two different approaches. And then finally, we tried to study the overall environmental impact of flexible operation by looking at how the two different operating modes performed in terms of water withdrawals by thermal power plants for cooling purposes, as well as water consumption through evaporative losses, and the overall system carbon emissions. And to study the economic performance, we looked at how the day ahead and real-time production costs varied for the different operating modes. So the next few slides are going to be full of numbers and a little bit heavy. And to just simplify things, I wanted to summarize the overall outcome of the study. And what we see is that by operating the system in a flexible way, in such a way that energy water resources such as wastewater and water treatment plants can help to provide operating reserves and load shifting capabilities, we were able to improve the overall balancing performance of the system, with net improvements in the average available load following reserves and ramping reserves, as well as a reduction in the overall time that curtailment is used in the whole year. And then we were also able to see significant improvements in water withdrawals, whereby the flexible case withdrew much less water for the study, and subsequently the water consumption through evaporative losses was also minimized. And on average, their CO2 emissions reduced significantly for all 6 scenarios for the flexible case. And finally, the economic performance in the day-ahead and real-time markets also improved significantly, with up to $70 million savings through flexible operation, as opposed to just the conventional operation mode that we currently have. So this figure here represents the operating reserves distribution for the load following reserves. I will only be looking at load following reserves in this presentation. And as you can see, what we want to focus on is the gap between the two profiles and the zero. So for a system that is performing well and utilizing the load following reserves well, you'll find that the profile is a lot farther from the zero, from the origin. And this implies that the system is not over-relying on load following reserves to balance itself. And you can see that for most of the scenarios, the conventional case is always struggling to using up a lot of its load following reserves in the balancing performance. And this table summarizes that result so we can see that in the flexible case, flexible water energy resources enhance the average load following reserves in all cases. And also you find that the minimum levels of load following reserves are not exhausted, are not zero for most of the cases. This figure represents the water withdrawal distributions for the two cases. And we can see that with flexible energy water resources, the overall water withdrawals is minimized through a greater utilization of renewable energy. So instead of curtailing renewable energy, you're using it a lot more. And this results in lower water withdrawals for cooling purposes for thermal power plants. And similarly, evaporative losses are also diminished and through greater utilization of renewable energy. And then finally, this here represents the CO2 emissions distributions for the different, for the two scenarios, with the red curve representing the conventional case and the black curve representing the flexible case. And we see that for the most part, flexible energy water resources cause a noticeable decrease in carbon emissions for all scenarios, actually. And day ahead costs, as you can see, on average, all cases for all scenarios, flexible energy water resources reduce their amount, reduce the total day ahead production costs. And this is evident in the overall reductions of the total cost reductions. And similarly, we see the same performance with real-time cost distributions. Just to summarize, we see that in New England, if we treated water resources as flexible, we're able to enhance the average minimum levels of load following reserves and ensuring that the system always has some operational capability to either meet uncertainty in demand or bring up to deal with uncertainty in demand. And we also see that the overall water withdrawals for thermal cooling are reduced just by virtue of greater utilization of renewables, and which displaces some of the thermal power plants for cooling purposes. And as a result, we also reduce the overall evaporative losses. And finally, we're able to see an decreased amount of decreased costs in the day ahead and real-time market production costs. So to conclude, we we started out by looking at how the electricity grid is changing. When we used to have this fairly standard electricity grid with a few centralized generation facilities that were designed to serve fairly passive loads. But now we have a lot of different drivers that are pushing the evolution of the electricity grid. One is decarbonization, whereby we are trying to reduce the emissions in the energy in the power system. And this has led to an increase in renewable energy installation. And then we have a growing demand for electricity, either through electrification or electrification of other sectors such as transportation, as well as heating. And then the regulation of electricity markets, active end user participation, and digital innovations in the energy technologies. And we see that with these drivers, the way the electricity grid is managed has to change in order to accommodate the complexity that comes with these new additions. And therefore, we need holistic techniques that will allow us to integrate multiple layers of control of the electricity grid at different timescales to allow us to manage both the technical and reliability requirements of the power grid, as well as the economic objectives. And for this study, we looked at how we can improve reliability or reduce grid imbalances and hence improve the overall flexibility for system operators by engaging demand side resources. And we focus specifically on energy water resources. And we saw that by adding small amounts of energy water resources, we were able to see significant improvements in balancing performance, the environmental performance, as well as the economic performance of the electricity grid. And so going forward, we would want to see how we can engage more demand side resources, especially with the emergence of energy Internet of Things. We could work on distributed transactive energy control at the distribution level to engage demand side resources in providing flexibility to electricity system operators. With that, I would like to acknowledge Amro for their support in the capacity expansion to come up with the 2040 scenarios that we use for this study, and the DOE for the funding. And I would also like to thank my lab at Thea for all the work and support during the study. And here are our references. And thank you. I will take any questions that you may have.
Thanks, Steffi, for the great presentation. I wonder how can you elaborate a little bit more regarding how you use water and wastewater treatment plants as operating reserves in your framework?
So we had wastewater and water treatment plants. We mostly looked at how much electricity they consumed. And we were able to incorporate the electricity demand for these resources in for the different load zones that we looked at. And we would allow, so wastewater treatment plants were able to reduce their production at different times of the day, and they were compensated for this reduction in their demand. And if you remember my example of how load following reserves are treated, you would have a certain capacity and you're able to move up or down. And if a wastewater treatment plant for example, is consuming 500 megawatts, and you can you can allow it to either reduce that consumption to a certain level, and that would count towards downward load following reserves. And you will compensate that resource for being flexible and contributing to dealing with grid imbalances. Does that help?
Yes, thank you. I guess a follow-up question is, how did you determine the minimum and the maximum capacity regarding how much water and wastewater treatment plants can go?
So we worked with Amro on this to get the data that we used for this study, and they had run several models already on the performance of wastewater treatment plants, and they provided us with that data that we used for this study. In terms of how much capability of ramping up and down, we had to make a guess. One of the biggest challenges that we had for this study was this lack of data. And so we had to make a lot of assumptions to in terms of how much a water treatment plant is able to ramp down and still be able to meet its performance metrics. And so we did like at 80, like at some points during the day, it's able to reduce by 20%.
Great, thank you.
You're welcome.